Hey students, welcome back. This is 6.6. This is Introduction to Enthalpy. So we're going to be talking about enthalpy here. You can read about this in 7.6, and we do have two homework problems to do. We still are going to be using Q equals MC delta T, and let's just jump right in. All right, so first starting off by enthalpy, defining enthalpy for our purposes. For the purposes in this class, we are going to define enthalpy as heat. Oh my goodness, I know. It's abbreviated by H, but we're going to call it heat. And so we're talking about like energy being transferred is really what it comes down to. Again, for our purposes, we are going to assume that our delta H is equal to our Q, which is heat, at a constant pressure, because for the most part, in this class for sure, all of our processes will be done in atmospheric pressure, which means our pressure is constant. Okay? So, let's jump on and can kind of continue on this. We've actually talked a little bit about this already, but let's make sure we've got it. So, signs on delta H when we have an endothermic reaction. Remember, the sign is positive. And we talked about that because energy is being added to the reaction. Alright? And we could also say it's being added to the system, right? Maybe that'll help us understand it. We're adding it to the system. Our products are at a higher energy than our reactants. So when it is exothermic, we have a negative sign, and that's because energy is being lost by the system. And maybe we should say released, not lost, because people maybe visualize that as like, woo, out there. Alright? Okay, so rolling on here. Hopefully that makes sense. Now, let's kind of talk about the stoichiometry. So this is very much like stoichiometry, all right? So basically our delta H reflects how much we have, which makes sense. If we think about that, like my car is dependent as well on how much I have. If I have 12 gallons of gas, I can go further, right, and have more of a reaction than I could with 6 gallons of gas. So that's kind of the same thing here. So let's kind of take a look at how that works. But again, it's all about a stoichiometric relationship. So if you're good at stoichiometry, you shouldn't have a problem with this. So we have a gas tank, barbecue. It contains 13.2 kilograms of propane. There's our propane. And we're supposed to calculate how much heat is released if we burn off all that propane. And here is our reaction. Something new for this unit is this delta H of reaction. We're going to see those delta H's there. If we see that negative sign, we see and we know it is exothermic. All right, so let's kind of take a little peek and look at how this works. So first, we've got to get from kilograms of propane to grams of propane. So blow this up a little bit. 13.2 kgs of propane, C3H8. All right, we'll have ourselves a little stoic line here. All right, kilograms to grams, we know that 1 kilogram equals 1,000 grams. You could have also just moved it a couple of, 3 decimal places, right, to the right, but we'll be all right. Now we need to get to moles because this is kilojoules per mole of propane. So we need to go from grams to moles, and we do that by dividing by the molar mass. Kind of as in a little aside here, C3H8, if I take 3 times 12 plus my 8 times 1, add those up, we could go a little bit further, but we get 44.09 grams is our molar mass of C3H8. And we've got 1 mole up here. That's what we did right there. Okay? So 1 mole of C3H8. With me on that? Okay, so now the stoichiometric relationship from our balanced chemical equation. For every mole of C3H8, forgot my mole. All right, for every mole of C3H8, I give off negative 2,044 kilojoules. And so that'll tell me where I'm at. So let's see what we get here. Locate my calculator. So we're going to take 13.2 times 1,000 and then times that 2044, negative, right? And then divide by 44.09. We're going to get a rather large number, And we're going to go, if we have how many sig figs? 3 sig figs because of the 13.2. So we're going to say -612,000 kilojoules of heat. That's how much energy we get from that one little propane tank, which is kind of impressive. Okay, awesome. So let's keep rolling. So now we're talking about how are we going to do this in the lab? What would this look like in the lab? And what we create is what is called coffee cup calorimetry. So literally you use a coffee cup. Those little styrofoam cups, a lot of times you might use 2. I see now that they actually have like made these and you can buy these, but for the most part you're going to use 2 styrofoam cups put together with a lid on it. And then you have a thermometer in there. And your solutions in there, and that's really all it takes. We have a styrofoam cup, maybe 2, depending on how you feel. The thermometer, and sometimes a stir, but sometimes you just do a little swirling action. All right, so let's see how we can relate Q and delta H here. So we keep rolling. We've got magnesium metal reacts with hydrochloric metal. There's our reaction. In an experiment to determine the enthalpy change, we used, let's highlight our important stuff, 0.158 grams of magnesium metal. All right. It's combined with HCl, 100 mils of HCl in a coffee cup. The HCl is sufficiently concentrated so the Mg reacts completely. So Mg is our limiting reactant. All right, that's our limiting reactant. The temperature rises from 26 to 32.8 as a result. Find the delta H of the reaction. As written, we know that the density of water is 1.00 and we know our C there is that. So what we've got to do is we've got to figure out how much energy was gained by the solution to tell us how much was given off by the reaction. Okay, so we'll start there. We're going to find Q of the solution. That's what we're working on right now. We know our mass of the solution. Well, we don't know our mass just yet. Let's figure that out. Our mass of our solution, we have 100 mils, right? And we know the density. So if I take 1.00 grams per milliliter, now we know the mass of our solution. We have 100 grams of solution. So there's our mass. We know our specific heat is 4.18. And we know our temperature change. It went from 25 to 32, so we're going to subtract those 2, right? And we're going to take 32.8 and subtract 25.6. All right, and now we're ready to calculate. I'm going to lose this for right now. Hopefully you have that written down somewhere. Maybe not below, like Miss Griffith did. That wasn't the smartest thing she's ever done. All right, so we find our Q there. We're going to take 100 times 4.18 times our difference in temperature, which I think is 7.2. All right. And we get 3009.6. Q of the solution is 3009.6, and that's our joules. All right. So that's how much energy was given to the solution. So that other part is Q of the Mg, right? This is equal to Q of the solution. So we just put a negative sign on it to get us our Q of Mg. So we've got negative 3009.6 joules. All right, with me so far? Cool. Now we need to find our delta H of the reaction. What we need to do first is we're trying to find our delta H is measured in kilojoules most of the time per mole, or in this case, since we have joules right here, we're looking for joules per mole. So our first step, as an aside, is probably to take this 0.158 grams of Mg and convert that to moles of Mg. So we know the molar mass of Mg is 24.31 grams. 1 mole of Mg there. And we'll do our calculation there. 0.158 divided by 24.31. And we get 0.00 6499, kind of keep them all for right now. And that's how many moles of Mg we have going. So now if I just want my delta H, which is in joules per mole, all I have to do, man, my writing, whew. Let's try that again. Let's just try that completely over. We're looking for joules per mole. So we know our joules, negative 3009.6. And we know our moles, 0.006499. And this will tell us what is on that reaction, or what gives us on that reaction. So let's see what we got. 9.6 and divide by 0.006499. And we get, negative 463,000 joules per mole, right? We could put that in kilojoules. We could say negative 463 kilojoules per mole. That would work as well, but it's kind of up to you, however you feel about it. Awesome. Great. See you next time.